Okay, so here, just looking at that equation, I can tell it represents a limacon without a loop. When I compare, now I have to compare the absolute values of these two. So the A value is -3, but its absolute value is 3. That is larger than the B value of 2. Okay? And when we're all done, we'll see how that negative affects the graph here, if at all. All right? Okay, now I see sine in there, and that tells me my symmetry is going to be with pi over 2. Theta equals pi over 2, so let's draw that in. Okay, so when we go to choose values to plug in for theta here, we'll want to pick angle measures that are on one side of that. So I would probably choose first and fourth quadrant angles. Okay, so let's do the first quadrant ones first. Make a big, large table here. Okay, so let's just start with 0. That would be -3 plus 2 times sine of 0, which is 0. That's going to create a -3. Okay, so if I plot that, that ends up actually putting me over here since it's negative, right? All right, next, pi over 6. That would be -3 plus 2 times sine of pi over 6, which is 1/2. So -3 plus 1, or -2. Okay, so right there is the line or the terminal side of pi over 6, right? So we got to go back in the opposite direction 2 units. That'll place me right there. Okay, we'll do pi over 4 next. It's -3 plus 2 times radical 2 over 2. Those are obviously going to wipe out. -3 plus radical 2, that approximates to -1.6. All right, so again, this is the terminal side of pi over 4. We've got to go back in the opposite direction of that to -1.6. Pi over 3 next. Okay, that's going to be radical 3 over 2 when you evaluate it with sine. So these wipe out. -3 plus radical 3 gives you, I've got it at -1.3. Okay, so right there's the terminal side of pi over 3. Go back 1.3 in the opposite direction. Okay, then we've got pi over 2 next. This is -3 plus 2 times 1, which is going to give me -1. Okay, so here is pi over 2. Go back 1 unit in the other direction. Okay, so right there we should start to see why this is not behaving the same as the cardioid. Okay, in the cardioid, that 2 would have to be a 3, so that in this last calculation, if this were a 3 here, 3 times 1 would be 3, add it to the -3, you'd end up with a 0, which would pull that pole into the, that point into the pole, right? Okay, so that's the difference here between the limacon with no loop and the cardioid. Okay, now I've exhausted first quadrant. Now let's go to fourth quadrant. Okay, let's actually do 3 pi over 2 next, or 270. That's going to be -3 plus 2, so sine of 3 pi over 2, that's negative 1, isn't it? That's going to simplify to negative 5. So rotate the 3 pi over 2, go 5 in the opposite direction. That's going to put you way up here. Okay, next let's go in the fourth quadrant. How about we use 5 pi over 3, or that's 300 degrees. So negative 3 plus 2 times sine of 5 pi over 3, that's going to be negative radical 3 over 2. So this is negative 3 plus negative radical 3, which approximates to negative 4.7. All right here is the terminal side to 5 pi over 3. Go back in the other direction, 4.7. That's going to put you right here. All right, and then 2 more points and I think we'll be good. Let's go 7 pi over 4, or 315. Sine of that is negative radical 2 over 2. So negative 3 minus radical, negative 3 minus radical 2 would be negative 4.4. Okay, so here is 7 pi over 4's terminal side. Go backwards from there, 4.4. Okay, and one more for good measure, 11 pi over 6, or 330 degrees. Sine of 11 pi over 6, that's negative 1/2. So this one will work out nicely, negative 3 plus negative 1, so we get a nice negative 4. And that'll plot right there. Okay, now all you got to do is take all those points, reflect them over that line of symmetry, and then we'll be able to sketch this. All right, just do your best with it. So if you start at 0, could draw it like that. But notice the way I actually drew the curve, that's not how it's sketched out, right? Like the starting point when theta was 0 was over here at this point, this point right here. And then we moved in that direction. So it would have actually traced out a little differently. Okay, now this graph is identical when you just look at the final finished product. That is the exact same graph as if this were positive 3 plus 2 sine theta. But the points don't plot the same way, okay? So think if that were positive 3, then this very first point would have been 0, positive 3. So instead of being there, it would have been over there, right? So it's just a matter of everything's been reversed. Okay. Questions there? All right. Next one. Let's do one with a loop now. These are the fun ones. Okay, so we're back to this one's cosine. So I'm back to having symmetry with the polar axis. Theta equals 0. Draw that in. I know this one's going to have a loop to it because my A value of 2 is smaller than the B value of 3. Okay. And because the symmetry is now with the polar axis, I'm going to use first and second quadrant angles. So let's start with 0. 2 plus 3 times cosine of 0 would be 2 plus 3 times 1, or 5. So right away, I got a point there. Okay. Cosine of pi over 6 is radical 3 over 2. Okay, if you want your calculator to approximate that, I've got it at 4.6. Should be right about there. Cosine pi over 4 is radical 2 over 2. This will approximate to 4.1. Use pi over 3 next. That's 2 plus 3 times 1/2. That's going to end up being 3.5 exactly. And I'll jump to pi over 2. Cosine of that is 0. So I end up with 2 there. Okay, so now let's start using some second quadrant angles. How about I do 2 pi over 3 next? That's 120 degrees. Cosine of that is, what, negative 1/2? So that's 2 plus negative 3/2, that's 0.5. So that's going to plot right there. And then we'll go, let's do 3 pi over 4 next. Okay, the cosine off of that is now negative radical 2 over 2. And here's where we'll start to see why we get the loop. Okay, notice all the results so far have been positive for R.
Pardon this interruption. At this time, all remaining sophomores, please take your items to your locker and then head to the cafeteria for your lunch. Staff, I just got to report the current sophomores on the trip will be back at 10:55 and then reporting to 4:50. Thank you.
Okay, so here I get an R value that is negative. Okay, so I think the terminal side of 3 pi over 4, but now if R is negative, I go backwards. And I know it's very hard to plot because it's so close to the pole, but right about there's, right about here would be where that point is. And that's going to be this, the start of the loop. All right, just a couple more. Let's go 5 pi over 6 next. Or 150 degrees. Cosine off of that is negative radical 3 over 2. This is going to approximate to negative 0.6. And that's going to place me right about here. And then the last value I'll use is pi. That'll give me 2 plus 3 times cosine of pi is negative 1. So this ends up being -1. So if I plot -1 pi, that's going to put me right there. Okay, now reflect all your points over the line of symmetry. So starting with these two, I can reflect those over. And those are going to be more points to give me the loop. And I'll reflect the rest. Okay, and then I've also got this one to do. Okay, so we saw how this kind of traced out yesterday in the applet, right? If we start at that very first point we plotted 0, well, it's 5, 0. Start there, go up, come down. You're going to pass through that pole, start the loop, loop around, pass through that pole again, and then you can finish through all of these fourth quadrant points. Notice the length of that inner loop is 1 unit from the pole out to the furthest point of the loop, and that's the difference of A and B. Okay. Questions there? All right, now let's look at a couple other different types of polar graphs. So next we're going to look at some rose graphs. Okay, so on a rose graph, the reason we call them these is because they're going to look like flowers, petals of a flower. All right, and their equations are a little different. It'll be r equals a number a times either sine or cosine of a value n times theta. And we'll see that the value of n determines how many petals we have. So let's pull this up. Okay, so I have in box 1, r is a times cosine b theta, and I've got some sliders that I can use to adjust the values of a and b. All right, so let's start with the a value and see how that affects my graph here. So a is just responsible for how long each of the petals of the flower is. Okay, so currently I have A at 4. Notice the distance from the pole out to these furthest points on each petal is 4 units. Okay, what about B? Watch this. Currently B is at 2. Let's make it 3. So obviously it changes the number of petals. Okay, what about 4? How many petals there? 8. Okay, let's go to 5. 5 petals. Let's go to 6. How many petals there? 12. Okay, so this B value, whether it's even or odd, is going to determine how many petals you have. So we can see when it's an odd number, that's the number of actual petals you get, right? But when it's an even number, let's go down to there. We said when B was 4, we ended up with 8 petals. So what do you think the rule is here? When B is even, what do you do with it to give you the petals? Double it, yeah. Okay. All right, so let's put that all into the notes here. So we saw when n is odd, the rose has n petals. When it's even, the rose will have 2n petals. The petals have a length of a units. And another thing to notice, if you didn't in the illustration there, was the petals are always equidistant apart from each other. Okay, so there's a lot of symmetry happening within the graph. Okay. All right, so let's look at our example. Now we're gonna plot a bunch of points here. Okay, and I'm gonna try to color code each petal with a different color. All right, so on this one, I see that N is 2, which means there's going to be 4 petals. And those petals are all going to be a length of the A value, which is 3. So that's a good place to start. Okay. So let's do some first quadrant angles. I'm going to do those in blue. So let's start with 0. So that's going to be 3 times sine of 2 times 0, or that's just 3 times sine of 0, which is 0. So you get a point right away at the pole. Okay, let's go to pi over 6 next. So when you plug pi over 6 in, it gets doubled, and it actually turns to pi over 3. So sine of pi over 3 is radical 3 over 2. And that's going to approximate, after you triple it, to 2.6. Right about there. Oops, next one. Okay, next we'll use pi over 4. Well, it'll get doubled to become pi over 2. Sine of pi over 2 is 1. So we get a nice 3. And that point right there, that's going to be the furthest point on the petal away from the pole to match the fact that the length of the petal has to be 3. Okay, let's go to pi over 3 next. That's going to be 3 times radical 3 over 2. Which is another 2.6. Okay, so notice if I plug pi over 3 in, it gets doubled to 2 pi over 3, right? Sine of 2 pi over 3, that's in the second quadrant, but sine is still positive there, right? So I end up with positive radical 3 over 2 still. That's going to plot here. And then if I go to pi over 2, it gets doubled to pi. What's sine of pi? Takes me back to 0. Okay. So I'm back at the pole. So right here is the first petal. Okay. All right, let's pick another color. I'm going to use red next for the second quadrant angles. And this is where it gets unique. It gets very interesting how the graph behaves, all right? So let's try 2 pi over 3 next. So you plug that in. 2 times 2 pi over 3 will be 4 pi over 3. Sine of 4 pi over 3 is going to be a negative value, because that's in the third quadrant now, right? So 3 times negative radical 3 over 2, that's going to be negative 2.6. Okay, so right here's the terminal side of 2 pi over 3. You grab that for me? All right, again, right here's the terminal side of 2 pi over 3. I've got to go backwards in the opposite direction, 2.6 units. How was the field trip?
It's good.
Good? Okay. You survived without your phone?
Yeah.
Yeah. All right. Next one. Let's go 3 pi over 4. Okay, so 2 times 3 pi over 4, that's going to be really 3 pi over 2. Sine of 3 pi over 2 is negative 1. So end up with a negative 3 there, and that's going to plot. So right here is, that's the terminal side of 3 pi over 4, but because r is negative, we got to go backwards to here. Okay, wild guess. What do you think 5 pi over 6 is going to produce? Anybody? Yeah, negative 2.6, because there's symmetry in the pedal here. So you'll end up with 3 times negative radical 3 over 2 again to get the negative 2.6. And that's going to plot right there. Okay, and then if I used pi, it becomes 2 pi when you plug it in. Sine of 2 pi is 0 again. So we're back to the pole. So there's the second pedal. Let me do a better job of that. Okay, so isn't that interesting that after you draw the first pedal in blue, and that's a set of first quadrant points, when you go and you use your second quadrant angles, they end up plotting to be down in the fourth quadrant. Okay. All right, pick another color. Let's go green next. I'm going to use third quadrant. Okay, so let's go 7 pi over 6, or 210. So think when I plug that in, it gets doubled. 2 times 7 pi over 6 is going to be 7 pi over 3, which is going to take me back into the first quadrant. So I'm back to getting positive values again, right? So I'll get a radical 3 over 2. This will approximate to 2.6. That'll put me right there. Okay, 5 pi over 4. 2 times 5 pi over 4 would give me 5 pi over 2, which is going to be 1 again when you evaluate sine. 3 times 1 is 3. Plots there. Next, let's go to 4 pi over 3. Sine of 2 times 4 pi over 3 is going to be sine of 8 pi over 3. That's going to be radical 3 over 2 again. You get another 2.6. That'll put you right here. And then if you use 3 pi over 2, you're going to get 3 times 0 again, or 0. Okay, so there's the third pedal, and now we'll finish off the fourth pedal with fourth quadrant angles. And we're going to see this behave similarly to the points that were in red there. So if I use 5 pi over 3, let me just jump to it. This is going to give me negative 2.6. 7 pi over 4 is going to give me negative 3. 11 pi over 6, that's going to give me negative 2.6. And if we get all the way back to 2 pi, we'll get 0 again. Since all those R values are negative there, it's going to take me backwards from the fourth quadrant angles into the second quadrant. And there we have it. Okay, now let's go back to that applet from yesterday, just so you can see it all, traced out from start to finish. All right, so it was 3 sine 2t, right? graph. Okay, so we get the first petal. Speed it up here a little bit. And then notice how your second petal goes down into the fourth quadrant. Then you go to the third quadrant. And now you finish off with the fourth quadrant. Or the second quadrant, I should say. All right, one more. Bear with me here. I know it's long today.
Mr. Manager, I have a question.
Yeah, sorry.
Since like all the pedals are the same, like can you just copy it?
Yeah, so knowing that property, right? If I know that they're all equidistant and I know that, the orientation of the points is the same, yeah, once I get that first pedal, I should be able to use those properties to reason out the other.
What if you have like 5 pedals?
Okay, so that's where this comes into play. The petals are all equidistant apart, right? So what you could do is you could say, well, so like in this case, the furthest point on this petal was at, where was that at? Pi over 4, right? Okay. I know there's 4 petals. There's a total of 2 pi, or 360 degrees, in one revolution, right? So I'm going to divide that by 4. So 2 pi divided by 4 is pi over 2. So that means to get from this point to here, I have to rotate pi over 2, or 90 degrees, right? So if it was 5 petals, wherever that first point, that first petal's furthest point is, just take 360 or 2 pi divided by 5, and that tells you how many to rotate to get to the next one. Does that make sense? Okay, reason I wanted to show you it from start to finish, doing all 4 tables, is to show you the path of how the points plot from start to finish, right? Yeah. Okay, this last one's kind of unique as well. So this is called a limnoscate. We got to kind of hustle here. Okay, so limnoscate it's a Greek word. It means ribbon. Okay, and the way the points kind of trace out, it's kind of like you're tying a bow or you're tying a ribbon here. All right, and look at the makeup of the equation. R squared equals a squared sine 2 theta, or r squared equals a squared cosine 2 theta. So these are the only ones where r is being squared. Okay, these are going to graph to look like propellers. Okay, they'll have like loosely related to a rose graph, where in a sense it has like 2 petals to it. Okay, all right. So if I want to do r squared equals 4 sine 2 theta, well, to be able to evaluate this, I got to get r by itself. So I'm going to have to square root both sides and make this plus or minus the square root of 4 sine 2 theta. Okay? All right, so let's make a table here starting with the first quadrant, 0. So if I plug 0 in, 2 times 0 is 0. Sine of 0 is 0. So this is going to be plus or minus the square root of 4 times 0, which is going to give me plus or minus 0. So that's just a point at the pole, and I get it twice technically. Okay, I plug pi over 6 in. It gets doubled to pi over 3. Sine of pi over 3 is radical 3 over 2. So this is the square root of 4 times that. And that's going to approximate to plus or minus 1.9. So see, I'm getting 2 r values out of this because of the 1.9. So that's going to put me right about here in the positive case. But in the negative case, I got to go backwards. And that's going to put me right there also. Okay, I use pi over 4. That's going to give me plus or minus the square root of 4 times sine of pi over 2, which is 1. And that'll evaluate nicely to plus or minus 2. That's going to put me right there when r is positive 2, and right there when r is negative 2. Okay, and then this is the last one I'm going to have to do here, pi over 3. 2 times pi over 3. Evaluate that at sign, you get radical 3 over 2 again. That's going to approximate to plus or minus 1.9 as well. So I got a point there when r is positive, got a point there when r is negative. Okay, now, here's the key. We'll just write this out real quickly. Quadrant 2 and quadrant 4 angles, if you try to use those, they will produce imaginary results. Okay, so for example, if I try to use the second quadrant angle of 2 pi over 3, that's going to make r equal plus or minus the square root of 4 times sine of 2 times 2 pi over 3. Well, that's 4 pi over 3. Sine of 4 pi over 3 is negative radical 3 over 2. And what's going to happen there is you're going to take the square root of a negative, right? So you will not get any points from second and fourth quadrant angles. Okay, well, what about third quadrant angles? They're going to produce the same points that the first quadrant angles did. So I'm done here, and this is how it sketches out. Watch. Like you're tying a bow. Okay, so really unique situation there with the square root.